Hi all, welcome to another video of the subject Power System Analysis based on KTU syllabus, and we are on module 2 and we were discussing on the topic unsymmetrical faults on power system through impedance. In the last video we have discussed the single line to ground fault, and today we are going to discuss the line to line fault on power system through impedance. So the presentation of the fault is as shown in the figure. Here the phase B and C are shorted through the impedance ZF. Okay, and we know that the representation can be done using 3 steps. Okay, 3 steps on each phases, and in the phase B and C these steps are shorted through an impedance ZF. And from the figure some assumptions can be made, that is the value of IA will be equal to 0, and this IB, okay, IB and IC are in a relation such that IB is equal to minus IC. And also we can say that VB, the voltage, okay, phase voltage VB minus VC, okay, the voltage VB minus VC will be equal to IB into ZF. Okay, IB into ZF. Okay, VB minus VC is equal to IB into ZF. IB into ZF is the voltage drop across the impedance ZF. Okay, so these are the assumptions can be made. So you can see here. Okay, so VB minus VC equal to IB into ZF. So from that VC is equal to VB minus IB into ZF. Here IB is equal to minus IC, or IC is equal to minus IB. Okay, and if you are substituting the values in the symmetrical compound equation of the current, okay, IA0, IA1 and IA2, the value of IA is equal to 0, and instead of IC we have written minus IB here. Okay, so by solving the matrix equation we will get IA0 is equal to 0, and IA1 is equal to 1 by 3 into A into IB minus A square into IB. IA2 is equal to 1 by 3 into A square into IB minus A into IB, which means this IA2 is equal to minus IA1. So this equation is a very important equation. That is, from that equation we understood that the negative sequence current IA2 is just opposite to that of positive sequence current, which means which indicates a parallel connection of sequence network in the sequence network of an fault. Okay, so here IA0 is equal to 0. Okay, so the 0 sequence component is absent here, and IA2 is equal to minus IA1, which indicates a parallel connection. Okay, so we can discuss later that. And the line currents, okay, the line currents IA, IB and IC can be obtained using this equation. So here this 1 by 3 is not there. Okay, 1 by 3 will not be there in that equation. So IA, IB, IC, matrix IA, IB, IC is equal to 1, 1, 1, 1 A square I, 1 A square into IA0, IA1, IA2. So we are substituting IA0 equal to 0 and IA2 as minus I1 here. Okay, so from this matrix equation, that is, we will get, okay, we have to find the fault current. So fault current here, the fault current is equal to fault current will be IF is equal to IB or minus IC. Okay, so from that the IB, we can obtain the equation for IB as just multiplying this row 2 with this column. So we will get as IB is equal to A square into IA1 minus A into IA1. Okay, A square into IA1 minus A into IA1, and if you are taking outside that IA1 into A square minus A. Okay, so here for getting we can substitute the term A, which means A, we know that it is 1 angle 120, and A square it is 1 angle 240. So in rectangular form we can represent that A and A square like this. Okay, so we are substituting that values here. So IA1 into minus IA2 minus J root 3 by 2 plus 1 by 2 minus J root 3 by 2. That is, A is minus 1 by 2 plus J root 3 by 2. So here it is minus A. So equation becomes like this. Okay, so 1 by 2 cancelled, and we'll obtain minus 2J root 3 by 2. So 2 cancelled, and we will get as minus j root 3 into IA1. So IB will be equal to, that is, we can say the fault current will be, okay, of course the fault current IF will be equal to IB is equal to minus j root 3 into IA1. Okay, and when we are talking about the voltage equations, the symmetrical component of voltages, okay, can be found using the equation 4.89. This is the equation, all we know that, and in that we are going to substitute the equation for VC. Okay, VC, we know that it is VB minus IB into ZF. That is, from this equation VC is equal to VB minus IB into ZF, that we are substituting here instead of this VC, and by multiplying the matrices, we will obtain the equation for VA1. VA1 is equal to 1 by 3 VA plus A VB plus A square VB minus A square IB into ZF. So by solving that, we will get 3 VA1 is equal to VA plus VB into A plus A square minus A square into ZF into IB. And from row 3, VA2 is equal to 1 by 3 into VA plus A square VB plus A VB minus A into IB into ZF. So by solving that, we will get 3 VA2 is equal to VA plus VB into A square plus A minus A into ZF IB. Okay, so consider these two equations, 4.91 and 4.92. Okay, so subtracting that equation, that is 4.92 from 4.91, we can write as 3A1. Okay, 3 VA1 is minus 3 VA2 is equal to, just substitute the equation for 3 VA1 and 3 VA2 here, and from that this VA and VB terms will be cancelled each other, and we will get it as minus A square plus A into ZF into IB. Okay, so instead of that minus A square, we can write as 1 by 2 plus J root 3 by 2, and plus A means minus 1 by 2 plus J root 3 by 2. So 1 by 2 cancelled, and we will get it as, in the bracket itself we will get as J into root 3. Okay, of course we will get J 2 root 3 by 2, so 2 cancelled, and we will get as J into root 3 ZF into IB. So VA1 minus VA2. Okay, if you are talking about VA1 minus VA2, so it will be equal to VA1 minus VA2 is equal to J root 3 ZF IB divided by 3. Okay, these 3 can be taken outside, and we can place that 3 here. Okay, and this is the equation for VA1 and VA2. J ZF IB by root 3. Okay, so 3 and root 3 cancelled, and root 3 comes in the denominator. And if you are substituting the value of IB from these equations, IB is equal to minus J root 3 IA1. So here substitute the value of IB. Okay, so VA1 minus VA2 is equal to J 1 by root 3 ZF. Instead of this IB, just substitute minus J root 3 IA1. So VA1 minus VA2 is equal to ZF into IA1. Okay, so this equation, that is VA1 minus VA2 is equal to ZF into IA1, which shows that in the previous so many conditions, we assumed that is if VA1, okay, if you get VA1 is equal to VA2, we can simply place the positive and negative sequence as in parallel. Okay, so here it is VA1 minus VA2 is equal to ZF into I1. So an ZF, okay, an impedance ZF comes between this VA1 and the VA2. Okay, so this equation, okay, this VA1 minus VA2 into ZF into IA1 equation, and this one, okay, IA2 is equal to minus IA1 equation. So these two equations suggest a parallel connection of positive and negative sequence networks through a series impedance of ZF. So the equivalent circuit of power system under line to line fault can be drawn like this. Okay, so VA1 and VA2 are connected in parallel, and a component ZF is in between that. Okay, and of course IA1 is equal to minus IA2. So IA1 is, we assume that IA1 is flowing here, so IA2 will be minus IA1. Okay, so this is the equivalent representation of our circuit, and from this circuit we can write the equation for IA1 as, okay, the IA1 will be equal to VPF divided by all the impedances, that is Z1 plus ZF plus Z2. Okay, so this is the equation IA1 is equal to VPF by Z1 plus Z2 plus ZF. Okay, and the fault current, of course, we have already found that IF is equal to IB is equal to minus J root 3 IA1. Okay, so IA1 will be VPF by Z1 plus Z2 plus ZF. Okay, I hope all of you understand the line to line fault on a power system through impedance well. So thank you.